Okay. So, complex numbers. Actually, we should talk a second. You remember back when we did all the sets of numbers? We had the naturals, the wholes, the integers, the rationals, the irrationals, and eventually we ended up putting a big back box around all of it and ended up with the what? The reals. So then we said everything is real. And now we know everything is not real, because now you know you can have square roots of negative numbers, so now you know that you could also have imaginary numbers. So, is there anything that's all numbers? Well, since I said we're going to talk about complex numbers, could there be a connection? No connection whatsoever. Okay, complex numbers. Okay, well, actually, what's a complex sentence? Yeah, has two. You got your two clauses here. Okay, complex numbers have two parts. Okay, so you're going, how can a number have two parts to it? That's a little weird. It's one number, but it has two parts. Well, in math, it seems like all things are possible. So, what's that color? That's a cool color. All right. So, complex numbers have two parts. They have a real part, and they have an imaginary part. And you kind of have to see this for that to make sense, because it's like, how could they have both a real and an imaginary? When we write a complex number, the general form is a plus bi. That's one number. Even though it's got a plus sign in the middle of it, it's one number. You have the first number part of it will be a real number part. The second part of it will be an imaginary part. So, for example, if I gave you the complex number 7 plus 5i, that's one number. Looks like two parts, but that's one number. It's got a real part, it's got an imaginary part. Negative 1 minus 19i, that's another complex number. It's got a real, it's got an imaginary. Now here's my question. Is 8 a complex number? Why do you say it can be? You're close. Yeah. It could be 0i. If I can add a 0i on, doesn't that make it be in complex form? So therefore that means every real number could be written as a complex number. So therefore all reals are actually complex numbers. And the same way, if I gave you negative 7i, that's an imaginary number. Can I make it be complex? Yeah, put a 0 in front, 0 minus 7i, now it's complex. So therefore, we can put a big box around all our sets of numbers and say everything is a complex number. All numbers can be written as complex numbers. Ooh, see, go home today, tell your parents you learned a new number. People will think that, oh, we know all the numbers there are. Heavens, you learned all the possible numbers there were clear back in elementary school. And then there was pi. Now there's complex. And later this year we'll learn the number e. Okay. Now, the good news is complex numbers work exactly the same as the problems you just did with square roots, because that I is a square root of negative 1, so it follows the exact same rules you know about square roots, how we work them. You're going to find most of this is very common sense. So, in fact, our goal for the rest of the day is to figure out how to add, subtract, multiply, and divide complex numbers. This is not a shock. You can do this from pure common sense. If I gave you 2 plus 3i and tell you to add it to 9 minus 7i, what is your gut instinct on how you might add those? parts, add the imaginary parts. In other words, add like terms. All you're doing. 2 plus 9 is 11. 5i plus negative 7i is negative 2i. That's all you're doing. Add the reals, add the imaginaries. I'm sorry, did I insult your intelligence with that one? And okay, equally difficult. What if I asked you take 6 minus 8i and subtract 3 plus 2i? How do you suppose you subtract them? Yeah. Now this one you've got your choice. I don't care which way you do it. You can sit here and look at them and just subtract them. Or if you'd rather, you can change this to a plus. Whoops, I didn't change color though. We can make this a plus, and you can change all your signs, and then you can add them. Whichever way works for you. I don't care. So then in this case, I would have, 6 minus 3 is 3. What's negative 8i minus 2i? Thank you. Negative 10i. Yeah. Woo! There's addition and subtraction down. Blew you out of the water on that one, huh? Okay. Multiplication. Has somebody already seen it coming? I want to take 7 plus 3i times 5 minus 4i. What do we usually do when we have two terms? It's not, you're not that lucky. It's not like terms. It's FOIL. I told you you're going to FOIL like crazy from now on. So, yeah, you just FOIL it. The only thing you have to watch out for is last. Just like last were a bit of a problem with square roots, you got to be careful with last on complex numbers. So, okay, first, no big deal. That's going to be 35. Outside your what? 8.8i. Insides are positive 15, okay? And then be careful, what are last? Yeah. The last, because you're going to have an I times an I, you will always get an I squared back there. Okay, now this, there's also a common step you'll do here. What did we know I squared became in that list of powers of I? I squared is always negative 1. So if I squared is negative 1, yeah, it makes plus 12. So every time you get an I squared, just cross it off, change the sign. So you actually just have 35 plus 12, which is going to be 47. And then add your I terms, which would be negative 13i. And ta-da! You have multiplied. We're good so far. All right. One other that's going to come up that's very, very similar to that. Now you see people mess this up. Actually, I see you mess this up not just with complex numbers. We mess this up all year. If I throw my pen across the room. Okay. What does it mean to square something? Times it by itself. So in the case of a complex number, thank you, Nick. Yes, it means takes it times itself. So yes, FOIL it. So, or if you know how to square, you remember the rule for squaring a binomial? That works here too. I don't care which way you do it. But the key thing is that if you write it out twice, I always have some people who try to turn it into conjugates. They'll do one with a minus and one with a plus. Squared means times itself. 2 minus 7i, 2 minus 7i. Don't change the sign in the middle. And then, yes, you really do have to FOIL it. But what do you know will happen with the outers and the inners? They won't cross out because they're the same signs, but you'll get the exact same thing. Minus 14i twice. And then last will be 49i squared. So then, yes, you'll go, oh, yeah, I squared. Cross it out, make it negative 49. And so 4 minus 49 is negative 45. Subtract my i's. And you squared it. So basically, if you see 1 over squared, it means you're foiling it. All right. Wow, and amaze me with your vast knowledge here. Division is coming. It's exactly the same as yesterday's square root. Identical. You do it the same way. How did you yesterday, if you got a single square root on the bottom, how did you get rid of it? You times by that same square root. Okay, so in our case, if I gave you, say, 5 over 3i, I is a square root. You can't have I in the denominator, so how are you going to get rid of it? Okay, you actually don't even need to do 3, you just need times by the I. So what will I get up top? 5i over 3i squared. And then immediately you're going to go I squared changes, cross it out, change the sign. So you end up with negative 5i over 3. So identical, and I is a square root, so you just do it the same way. Which should then have you immediately going, well, I'll bet when she gives us one with 2 terms, what? Wait, I heard conjugate. One's correct, both are correct. I am going to have to FOIL something, and what is it I'm going to multiply? What am I going to multiply by that makes me FOIL? You're going to multiply by the conjugate of the bottom. So what's going to be the conjugate of the bottom? 5 plus 4i. So then, yes, you got to work out both top and bottom. Yay! Now, you want to do top first or bottom first? Top. All right. So I got 20. Outers are 16i. Got 10i. Okay, what are last? 8i squared, which I'm immediately going to go change to negative 8. And we'll add that up in a second. On the bottom, you get a shortcut. How do you shortcut? You know conjugates are going to cancel the middle terms, so you only have to do first and last. You don't need to do the middles. So firsts are going to be 25. Lasts are going to be negative 16i squared. So cancel it, positive 16, which now, that means your bottom's going to end up a single real number. You'll be rid of the i's. That's going to be 41 on the bottom, nice whole number. 20 minus 8 will make 12. 16i and 10i will make. Okay, then you should stop and ask yourself, can I reduce any of those? Is there any number in common to 12, 26, and 41? Don't think so. Sometimes there will be. And ta-da! You have divided. Woo! Doggy. Okay. So this last part is I just want to give you a taste of why you might care about this, to show you why we would do this. And believe it or not, I'm not actually going to have you do a whole lot with this, but you can graph a complex number. Now, how would you graph a complex number? Well, we're going to graph 2 plus 3i. Well, the difference is they changed the coordinate system. They call the x-axis the real axis, and they call the y-axis the imaginary axis. So if you want to graph 2 plus 3i, the real number is 2, so it means you go over 2 on the real axis. And what do you suppose I do with the plus 3? Up 3. Up 1, 2, 3. So over 2, up 3, that's the point. A complex number is not a point. It's a thing known as a vector, which, should you take physics or you take trig, we go do a whole lot more with vectors. But a vector is a line segment that starts at the origin and it goes out to that point. It stops there, but it actually moves. It has a direction. Vectors have tons of uses out in the real world. So it's actually drawn out there. A real number represents, or a complex number represents a vector. So, just, can't remember if I asked you this on your journal or not, but I'll write it up here just in case. A vector is a directed line segment. Well, what I want to show you is I want to show you one of the coolest, I guess, I call it a new discovery for complex numbers. And I got to go load it in a second for you. Back up. Out of my way. Obviously, I have too many folders. Whoa, why'd you go small? See? Okay. Have you ever heard of a fractal? Have one who's heard of a fractal?
My brother had he had to add 1 to 100 fractals before he can count from 1 to half.
Okay, I'm not quite sure what that would mean, but okay. This is the world's most famous fractal. It's known as the Mandelbrot set. It was actually discovered around 1980. It is a computer-generated image. But what it's doing is it's a graph of complex numbers. The x-axis is going right dead center through right down the middle of this thing. The y-axis is not straight through the top and bottom bulb, but it's a little bit off center, because the y-axis is about right in there. Okay, and you're going, why? Who? The guy who discovered his last name was Mandelbrot. And it was, at the time, they were just incredibly beautiful, because a fractal has certain characteristics. If you look at a fractal is what we call self-similar. And I need to get that on the notes. If something's self-similar, that means if you zoom in on it, you find it inside itself. And so I'm going to show you here, believe it or not, if you start zooming in on this thing, you will find more of these shapes inside it. In fact, can you all see that black spot right there? Up here I can see it better. But if I tell it to zoom in on that, and yikes, I don't know if it's going to let me do it with this pen. Nope. I need a mouse. So if I zoom in on that, whoa, geez, where'd you go? There we go. If I zoom in on it, you can see that it's a baby Mandelbrot set. And if I keep zooming, look, there's another one. Oh, it's going to give me trouble with that, though. I don't know if it'll let me go. There, zoomed in is another one. And if you keep zooming in on it, you'll keep finding itself. Well, these are actually quite beautiful images. I want to make it. This is not. Will you let me zoom in on like down here? Yeah. As you zoom in on the edge, you can see that you get lots of little bulbs. And if you keep zooming in on them, they're quite beautiful. And you can see different details. It actually turns out that if you study this, we do this at the very end of pre-calc. We do a last week and a half we spend on fractals. It turns out each of these bulbs on here represents a fraction. This bulb up here turns out represents a 1/3 fraction. This one over here is 1/2. The fractions, the bulbs are on here in numerical order. It's like a real number line going around this thing. The patterns they found are amazing with what's inside a fractal. And it's all computer generated. And what they do to create it, so you all can see where the real complex numbers come in. When they're creating that image, they pick one coordinate on the coordinate system. I'm going to pick this one. No, I don't want that one. Let me go this one. This one would be, let's pick this one. This one would be 0 over and 1 I up. It's 1 up. If they want to decide on a fractal what color to color that one, the equation that creates a fractal is always the equation x squared plus the point you're checking on. If you want to check that point, then that's what you put in there. And you do a process known as iteration. You take 0 and you sub it in for x. And you go, what do I get if I do 0 squared plus I? What do I get? 0 plus I would be, wouldn't it be I? Okay, when you do iteration, you take the answer you got and you put the answer in. Ah, right. Okay, I'll have to finish telling you that. You need that for your journal, but I'll finish telling you next time about fractals. It's amazing what happens here. Whoa, y'all should have